Today we're going to discuss the concept of air resistance. Now, in your exam, you're not going to be asked to remember any formulae or equations, but you're probably going to be asked to conceptually describe the effects of air resistance on motions of bodies or particles. Now, one of the easiest ways to discuss air resistance and its effects is the scenario of a skydiver jumping out a plane and opening a parachute. So, this skydiver, at the instantaneous moment in which he jumps out the plane, the only force acting on him as soon as he jumps out of the plane is going to be his weight. So therefore it's mg. The only force when he instantly jumps out of the plane is going to be his weight. So at this moment in time, which is at t equals 0 seconds, the instant that he just jumped out of the plane, this instant where he just about loses contact from the surface or from the floor of the plane, the resultant force acting on the skydiver is going to be equal to his weight. And therefore he will accelerate due to gravity. His acceleration is going to be equal to the value of g. And because he's accelerating, that means he obviously is going to be having an increasing velocity. So the velocity will increase downwards. And we're going to assume that when he jumps off the plane, he jumps off at rest. So he just seems to like fall off the plane rather than jumping downwards. So we're going to assume that he just falls from rest. Now, as some time elapses, we know that the velocity is increasing. And the one thing that you need to know about air resistance is that air resistance increases when velocity increases. After some time has elapsed, the air resistance acting on the skydiver is going to increase. So, as you can see in this scenario, the resultant force now acting on the skydiver is its weight minus the air resistance force. From this diagram, we know that the length of the arrows represents the magnitude of the force. At this moment in time, the weight is still greater than air resistance. So, this does still mean that the skydiver is accelerating downwards. However, because of the air resistance, this acceleration is lower. So, the acceleration at this moment in time will decrease due to air resistance, but the velocity is still increasing. So he's still getting faster, but he's doing so at a slower rate. Now you can kind of see that as the velocity is increasing and increasing, the air resistance is going to keep on increasing, up to a point where the force due to air resistance is going to be equal to the weight. So at this point here, eventually, air resistance is equal to the weight. And at this point, because the air resistance is equal to the weight, the resultant force is zero. And we know because of F equals ma, this means that the acceleration is zero. So if the acceleration is zero and the resultant force is zero, that means that the skydiver or the body is not going to be accelerating, and therefore it will travel at constant velocity. And because it's traveling at a constant velocity, the magnitude of that air resistance force is not going to change. So therefore it's going to keep at this constant velocity until something happens, like until another event or until it hits the ground. So we call this velocity the terminal velocity. If nothing else happens, then the skydiver is going to hit the ground at this terminal velocity. Now, in a real life scenario, this is where this skydiver, either at this point or it can be at any time after this point where he deems safe, because he's going to be traveling at this terminal velocity for the rest of his journey, he's going to decide to open his parachute. So at this point here, the skydiver now opens a massive parachute. And we know that there's still going to be some weight acting downwards. And now, when the parachute opens, due to its large surface area, the air resistance is going to increase drastically. So you're going to get a much bigger air resistance force. And in comparison, you're going to get the weight being smaller than the air resistance. So therefore, the resultant force in this case is still going to be the weight minus the air resistance. But because air resistance in this case is now bigger than the weight, the resultant force is negative. And therefore, the acceleration is negative in the downwards direction. So what that means is the skydiver will decelerate, or its velocity will decrease. Now, because it's decelerating, the velocity will decrease, and therefore that means that the air resistance will also decrease. And as time passes, eventually, air resistance will once again equal the weight. As air resistance decreases, it will get to a point where it's now in equal magnitude to the weight. So therefore, the acceleration of the body once again is zero, and the resultant force on this body is also zero. So it will once again travel at a constant velocity. And this is once again a terminal velocity, but this time it is of a lower speed to the previous one. So it's a lower terminal velocity. And it will continue to reach the ground at this velocity, and this velocity will be a lot safer to hit the ground at than the velocity it was previously travelling at. So let's look at what a velocity time graph will look like for this scenario. Initially, we said that the skydiver was going to be accelerating due to gravity and gravity only. So it's going to have quite a steep gradient, where the gradient of this line is equal to g. So this at this initial portion of the graph, the instantaneous gradient at the origin is going to be equal to gravity. Now we said that as velocity increases, air resistance increases. And that means that the acceleration is going to start decreasing, which means that even though the velocity is still increasing, it's going to increase at a slower and slower rate. So that means that the gradient of this graph is going to start decreasing. So it's going to look something like this. And eventually we said it was going to come and reach this terminal velocity, and it may travel at this terminal velocity for some time. So in terms of our figures, at this point is point 1, point 2 is when it starts to slow down, and point 3 is here when it's now traveling at that constant terminal velocity. Now when the skydiver opens his parachute, there's going to be a drastic change in the acceleration, because there's suddenly going to be a large increase in the air resistance. So you're going to see a sudden change in the gradient, and the velocity will start to decrease and decrease and decrease until it reaches yet another constant terminal velocity at a much lower speed. And with the parachute open, the skydiver will now hit the ground at this much safer velocity. Now let's go and revisit our old case of the projectile motion. So I'm projecting this ball from a cliff at an angle to the horizontal. So I'm projecting it in the air. Now in the first case of projectile motion, where we considered how this ball will travel without the presence of air resistance, we know it will take a path something like this. And excluding air resistance, we know it travels in this sort of path because it will travel at a constant velocity in the horizontal direction, and it will accelerate at the gravitational field strength G downwards. Now, with air resistance, no matter what direction it's moving in, the air resistive force is going to be acting opposite to its direction of motion. So therefore, when it's going upwards, the air resistance is going to be acting downwards. When it's going down, the air resistance is going to be acting up. And when it's going to the right, the air resistance will be acting to the left. So with air resistance, it may take a path of something like this. So with air resistance acts opposite to the direction of motion of the ball. So therefore, it will reach a lower maximum height and its range, which is this distance here, which is basically where it hits the ground, will also be lower. The reason for this, if we break it down into the horizontal and vertical components, when it's travelling towards the right, the only force acting on this ball horizontally is going to be the air resistance, and it will be acting in the direction opposite to where it's moving. So therefore it's going to decelerate. And because its velocity is decreasing in the horizontal direction, it will therefore land in the horizontal direction at a closer point to where it did before. Now when the ball is moving upwards, we know that the forces acting on this ball, well, firstly there'll be its weight, mg, but also the air resistance will be acting in the opposite direction to its motion. So the air resistance will also be acting downwards. So when the ball is travelling upwards, it usually does decelerate due to gravity, but it will decelerate even more with air resistance. Now when the ball is moving downwards, the weight will still be acting downwards, but this time the air resistance is going to be acting upwards. So the same thing will happen here as what happened to the skydiver. The ball will still accelerate downwards due to a net force or resultant force being in the downwards direction, but the acceleration will be lower, and at the point where the air resistance is equal to its weight, it will eventually reach terminal velocity. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.